Welcome to Ask and Learn.
In this problem, a cylinder is initially filled with saturated refrigerant 134, a vapor, at a specified pressure. The refrigerant is heated both electrically and by heat transfer at constant pressure for 6 minutes. The electric current is to be determined, and we will show the process on a TV diagram as follows. So we can see that with an increase in temperature, we have an increase in volume, and the pressure here is constant. Now we assume that the cylinder is stationary, and thus the kinetic and potential energy changes are negligible. The thermal energy stored in the cylinder itself and the Y is negligible, and the compression or expansion process is quasi-equilibrium. Now we take the contents of the cylinder as the system, and since the system is closed, we can write the energy balance equation. The energy in minus the energy out is equal to the change in energy of the system, delta E. So the energy in is due to the heat into the system plus the electrical work into the system. And the energy out is the boundary work. So that's a minus. And this is equal to a change in internal energy of the system, delta U. Remember that the kinetic and potential energy contributions are zero. So we can write this. If we take the boundary work across, we get the heat in plus the electrical work into the system is equal to delta U plus the boundary work, delta WB. But this is equal to M into H2 minus H1. So essentially the heat in plus the work done by the current, which is VI delta T, the power times the time, is equal to M into the enthalpy of state 2 minus the enthalpy of state 1, the specific enthalpies. And this is because, remember, for a constant pressure quasi-equilibrium process, delta U plus the boundary work is equal to the change in enthalpy. The change in internal energy plus the boundary work gives us the change in enthalpy of the system. Now, let's write down our properties at our given values. So we have P1, the initial pressure is 240 kilopascals. And this is a saturated vapor. And so the enthalpy of state 1, H1, is equal to the enthalpy of a saturated vapor, Hg, at 240 kilopascals. And so from our tables, this is 247.32 kilojoule per kg. For our final state, we have P2 is the same. So we have constant pressure, 240 kilopascals. And we have the temperature of 70 degrees Celsius. And so we get H2 is equal to 314.53 kilojoules per kg. So now we have our specific enthalpies of state 1 and state 2. So we can substitute this back into the energy balance equation, and we can find the current. So if we substitute our values in, we get 300,000, that's volt ampere seconds, plus 110 volts times I times 6 minutes, which is 6 times 60 seconds, is equal to the mass of the vapor, which is 12 kg, into the change in enthalpy, which is 314.53 minus 247.32 kilojoule per kg. And noting that 1000 volt amperes or 1 kVA is equivalent to 1 kilojoule per second. So since these are all in SI units, we get our current, which we wish to solve for, I, to be 12.8 amperes.